Well, hello everyone, and welcome back to Adrian's Digital Basement. On today's video, we're back on the Apple Lisa, and this is going to be part 6 in the whole series. So if you haven't caught up on the series, I recommend you do that first, since of course, as per usual with these long video series, I'm going to be picking up where I left off in the last part. Now to recap, this Apple Lisa was in rough shape. In part 1 I took it apart, battery damage had pretty much destroyed a couple of the boards and really wrecked all sorts of stuff in the computer. It turned out though that the CPU board and the RAM board were actually working, even though they had a little bit of battery damage on them. I visited Alex the cat, who tested both of those boards, and they both work great in his Lisa. So he sent me home with a missing power supply that I needed and some PCBs that I could rebuild to get this Lisa up and running. Then in a follow-up part, I built up the motherboard PCB that Alex had given me with some salvage parts and original parts, and then I rebuilt an I/O board since the one in the original Lisa was all damaged. And then in the last part, I finally got all of that stuff all assembled together, along with some new harnesses that I had to rebuild, and I was able to test the Lisa, and it actually came to life. It was a little hit and miss because of some power supply issues with the power supply that Alex had given me, but I was able to get those sorted and get the machine up and running. And that brings us to where we are today. So at the end of the last video, we had some issues. The machine was not passing its diagnostics for the disk drive controller. I was getting an error 57, so I got to dig into what's going on with that. In this video, I want to try to troubleshoot some of the issues the machine is showing when I booted it up in the last part, but ultimately I would like to try to get it booting Lisa OS or LOS to see if this thing is actually working. That's the true test of this machine, if I can boot into the Lisa operating system. So with all that said, without further ado, let's get right to it. This is pretty much where we left off in the last video. All the boards are installed into the motherboard, and a power supply, which is now working, it's connected up, and the RGB to HDMI is hooked up on the backside, and the system booted, and we were able to capture the video and see that it was actually running. It wasn't passing all its diagnostics, but at least it was trying to boot. Now with what I tested trying to boot this thing on the last video, there were 3 issues I was able to detect. The first is the light in the power switch wasn't working. The next thing I noticed that's wrong is that when this stopped booting due to a disk drive controller error, it should have created a multi-tone beep tone, I think like a high-low or something like that, and I didn't hear anything. I think I could just barely hear it, but it wasn't very loud. But the biggest problem, of course, is, as I just mentioned, that the disk drive controller circuit is not passing its diagnostics. When the machine popped up with that error, I did a little bit of Google searching, and I found a very detailed article on actually doing some diagnostics using the service mode that's already built into the Lisa, because there's a myriad of issues that can all be attributed to that error 57. For instance, the CPU in that circuit maybe isn't working, or, I mean, there's a whole bunch of issues that could be wrong. Now to run service mode, you have to use a keyboard, and that's something that I actually have now. This is a Macintosh keyboard, but I bought one of these adapters that allows me to plug any of these Mac keyboards, Mac Plus or Mac 128 keyboard, into the Lisa. And this should allow me, if of course the keyboard functionality works on the I/O board, to get into service mode so we could poke around a little bit and see if we could try to figure out what is causing the floppy drive not to work. A few other notes from when I last worked on this machine in the last video. Here's the wire harness that I built because the other one was battery damaged, and I actually found some correct 26-pin connectors in my stash of parts. So I was able to crimp those on, so that means if I ever get to the point where we could try to boot floppy disks, at least the cables are correct. Also, you might be noticing that I have the Lisa CRT driver board sitting here. And the reason why is because I figured out that if you turn on the Lisa without this connected, the 33-volt rail the power supply generates that goes to the CRT board actually kind of goes up to like 56, 60 volts without any load on it. So what I did is I connected my electronic load to that pin on the harness that should plug into this edge connector, and then that brought the voltage down to like a reasonable 36 volts while the system was powered up. So I'd rather run this with something connected to it, either my electronic load or maybe the original CRT board itself. So in order to do that, because this is obviously fully untested, and this is actually the one that came from Jared, what I did is I used my cap tester just to go through all the large electrolytics and some of the smaller ones. Everything tested perfectly, by the way. And then I checked for any broken solder joints, and I didn't really find any, although I looked at the schematic, and what's on this heatsink right here, this is the 25 volt regulator. That's what the 33 volts gets turned into. It's a linear regulator, and it was a little warm looking on the bottom. So I reflowed those joints as well, just because they might have had a bad solder joint, which is what caused it to have a little bit of a brown spot on the PCB. This thing actually looks fine. I don't really notice any issue. Now, I want to run the Lisa with this connected just so it presents some load to the power supply. But obviously I don't want to generate high voltage. I'm not ready to plug the CRT in and see if it's all going to be working. So in order to do that safely, what I ended up doing is just simply removing the horizontal output transistor. It lives on this heatsink, and without that part in the board, it's impossible for this thing to even generate any high voltage. Of course, a flyback transformer plugs into this connector, but I really didn't want to leave the horizontal output transistor on the board while this was disconnected, just in case it, I don't know, caused some kind of issue where it damaged that transistor. So it's just safer to take it out. And that way I feel that it's pretty safe just to run this thing connected as is like this to the Lisa power supplies to load it down so we don't have that runaway voltage rail anymore. Then the next little tidbit is that the motherboard and the card cage should be mounted on this metal plate. This came from the battery damaged Lisa. I just have one of these, and I briefly showed in the last video that I didn't really want to use this, which is why this is sitting on a mouse pad, because this was all covered in a bunch of battery corrosion and rust. So you'll notice it doesn't look so bad now, and that's because I put vinegar on here and then I hit it with the wire wheel on both sides. It's not perfect, but it's certainly a lot better than it was. And that makes me feel much more confident that I can mount the motherboard, the card cage to this metal plate, and I can get rid of this whole mouse pad thing. Eagle-eyed viewers among you may notice that I seem to have a button installed into the metal plate as well. This is what is going to be the reset button for the Lisa. I just found this in my spare parts bin. I did not have to drill the hole or change anything. This just literally fit right in perfectly. And once I cinch down the little nut there, I think this will be perfect. And once the motherboard's mounted into this metal tray, then I'll just run the wires from that switch directly to the 2 points on the motherboard. That facilitates the reset switch. Reset is basically just grounding a reset line that goes to the CPU board, which is the middle board, and that generates the reset that probably goes to the rest of the system. So I think the first thing I'm going to do right now is take everything apart so I can get the motherboard and the card cage properly mounted into this metal tray. And that means that this is one step closer to all sliding into the actual Lisa chassis. Yes, there it is. This thing is coming together. Everything is mounted properly in that bottom metal shelf thing, whatever it is, and I even have the reset button installed. Where I ran into a small issue, and it meant I had to take apart this whole setup again, was the motherboard. On the bottom of these D-sub connectors, there's a little like metal prong that sticks through the PCB. That's what basically grips the PCB. Obviously, the original ones actually had screws that you put down through the top. I don't remember taking those out, but they would have been there to give some strain relief to the PCB. If we tilt this over and we look at the bottom, there are riveted in, or however these are attached, little screw standoffs. Well, the problem is the little prongs on these D-sub connectors that stick through the PCB actually stick down about 1.5 millimeters, and those were interfering with those standoffs. So it was pushing the entire PCB up and sort of bending it when I put all the fasteners in. And I really noticed it because the RCA jack, which isn't really centered as it is, it's kind of up near the top, but it was pushed right up against the top, and it would have made it hard to even get an RCA cable onto there. So I took it all apart and I just snipped off all of those little prongs. I just used some flush cutters. And when I put it back together, the bottoms of the D-subs are touching those standoffs, but it's not pushing the entire PCB up. So now the PCB is sort of floating. It's not wedged against the metal structure of the tray. Now you may be noticing that there's a little 9-pin connector here. Now what this is actually a connection for RGB to HDMI. I was using this in the last video, and I didn't really talk about too much how this works. Essentially, this is picking up the horizontal vertical sync, ground, and the video signal off of the buffer chip that is on the motherboard. That happens to be this IC right here. So I did originally with this clip to get the RGB to HDMI signaling is I just clipped this on and had a D-sub connector. Well, I just wired up a ribbon cable onto the bottom side of the motherboard. I soldered that onto the pins, the same pins I was using with that clip. And I just ran that over to come out of the case in this spot. I know it's not really pretty, but I don't really know a better way to do it. I kind of realize now that probably what I should have done is just mount this on the inside of the case. So if you wanted to use this, you just have to pop the back cover off of the Lisa when it's fully assembled, then you could plug into this. As it is now, it's kind of silly, but whatever, I can fix that later. But it should hopefully work and be great for the bench testing that I'm about to do. Here's what it looks like on the backside. I hadn't really showed this since I was doing the bench testing with it flipped the other way. We have RAM card 1, 512K. It's in memory slot 1. There is a second slot. I can have up to 1 meg of RAM with 2 of these cards. There is a mod that you can do to convert one of these cards to, instead of using 64 kilobyte chips, it uses 256 kilobyte chips. It brings it up to 2 megabytes, which I think is the maximum the Lisa OS can actually address. All right, so it's really time to do some bench testing. So right off the bat, got to plug my ribbon harness into the system. So I wrote up just to help me know which way to plug that in. And there was one thing I did work on in between last video and this video is what was on the end of this harness was, I think, the power supply that went to the Twiggy hard drive, and it was all corroded. It had a bunch of blue stuff happening, and because I didn't want the corrosion to possibly leach down the cables, I cut it off, put heat shrink on each wire and zip tied it together. That way, this is just a kind of a dead end. And if I ever need probably 5 volts or 12 volts, that's likely available here, plus some other voltages. Maybe I should have added a Molex connector now that I think about it. If I ever want to put some kind of internal drive or something like that, I could use this. Anyhow, with this harness, it's this connector that is the main one that plugs into the motherboard. And you can really tell by the way the wire is dressed that this is the power supply connector, and this is the one that goes to the CRT board, which I'll be plugging in just a moment. Power supply is connected. The RGB to HDMI is back there. I have this 9-pin cable connected up, so I can plug this into the little 9-pin that I've added. I'm thinking before I plug in the CRT board, since this is completely unknown if this is going to cause the system not to boot or whatnot, I should just double check that everything is still working. When I just want to validate that this video connection is working to the RGB HDMI and everything with the motherboard is still good after all of the installation work I did putting it into this tray. So let's turn on power to the power supply. There it is, nothing happened. That's a good sign. Let's push the power button. Okay. Got a black screen on the RGB HDMI, that's good at least. Oh yes, okay, good, it's working. That 33 volt rail is gonna be way too high right now, but hopefully that is not a problem. Let's just let this run through the diagnostics in case anything has changed. No, we still have error 57. Let's see if the reset button works. Oh no, it doesn't. I wired it up to the wrong pins. The original switch has 3 pins. There's a ground pin, and then we have 2 different positions. One was like open and one was closed. I just hooked it up to the wrong one, obviously. I took a look at the motherboard and tried to see where the traces went, and I thought I hooked it up to the correct one, but clearly I did not. I have the multimeter set to continuity mode. I just want to see if the reset button is working, because I did solder these little connectors, or these little pins onto it. So I'm touching the 2 pins, and if I push the button, yeah, it beeps. Either there's a problem with the CPU card, which handles the reset circuit, which we know there is. It shouldn't take so long with that black screen before we get the boot screen with the graphics. So I think there's something wrong with the reset circuit on the board, and that's quite possible that's keeping the reset button from working as well. That is just another problem to add to the list. For now, I'm not going to worry about that. I'll try to figure that out at some point in the future. I forgot to even mention it in the intro to the video that, yeah, there's yet that problem as well. Time to plug this board in. Hopefully this doesn't cause a short or some other issue, but I guess we'll find out shortly, pun intended. I think I'm set up to measure some voltages on the large caps on the CRT board, which is just sitting back there. And I have it kind of upside down so I can probe the bottom side. So first things first, I'm going to turn on the computer, see if any smoke comes out. If you see any smoke coming out of the back, well, we know there's a problem with the CRT board. Okay, here we go, 3, 2, 1. Okay, well, the system is powered up. Let's take a look at this cap here. Uh-oh. Yep, smoke. Did you see it wafting up there? Oh dear. We got the smell of burned electronics, all right. Oh yeah, that's quite odorific. If I act quick enough, I can power up the thermal camera. Luckily it has battery power still. And I can hopefully see what got hot. Something over here in this area. I see what got hot and burned. It's R1. It's all black. All right, to the schematics. How funny my wallpaper says bang. Luckily, nothing banged. We just had that resistor that said, no, I'm done. There's just so many moving parts with the Lisa. I mean, it's not moving, so to speak, but you know, there's the CRT board, so many different components here. I need to try to focus myself, and like I'm going off on 5 different directions, but just this is a complex system and all these parts are completely unknown. This is the board from Jared, by the way. Yeah, nothing's bad on the bottom, but that resistor was unhappy. So the way the voltage regulation works, there's the 33 volts DC input. There is a tiny little capacitor, 0.47 at 50 volts, by the way. So yeah, if it was running at like 60 volts, that is too much. Here's a 7824 regulator. It has an adjustment pin that actually goes to the width coil. So it looks like the way the width adjustment works, on the Lisa at least, is using a potentiometer. It just varies the B plus or whatever this 28 volts. I'm not sure if it's B plus necessarily, but it's probably in the horizontal drive section. And there's R1, 120 ohms that just let go. So normally the 7824 is a fixed voltage regulator, but I think it references ground, which happens to be the middle pin on it. And it appears the way they're altering the voltage output on this from 24 volts to, I guess, plus or minus whatever, is by altering what the ground pin sees. So pin 2, that would normally be going to ground, and it goes through an adjustable potentiometer, this width one, and then it goes to ground through this 120 ohms. That's the one that burned. As you adjust this back and forth, it's just a voltage divider based on, well, the output. So I guess it's like a bit of a feedback circuit, and it allows you to raise the voltage up beyond 24 volts. Now, the odd thing is the regulator itself is cold to the touch. And I would think if there was a short circuit beyond the regulator on, say, the 28 volts, that this would be getting hot. I don't quite see why the ground pin burned the way it did. Here's the CRT board, just so you can see close up what that R1 looks like. There it is. And yep, it's a little bit burned. And there's that width potentiometer, the one that works in conjunction with that 120 ohm resistor to vary that ground reference all the way back to the regulator, which happens to be over here. Now this is the bottom of the regulator, and I did reflow it, so there's a bit of flux on there, but you can see it's a little bit burned. This is the high voltage that comes in, like 33 volts or whatever. The middle pin we know is that ground reference, which kind of goes off and over to that adjustment. And on this pin, this is the output. So if I check between the adjustment pin and the output, it's beeping my multimeter, but it's reading 30 ohms. Let's check between the input and the output. 20 ohms between the input and the output. That does not seem correct. And yeah, so between the adjust pin and the output, that's that 30 ohms again. And between the input side, which is where the red probe is, and the middle pin, or which should be ground, 17 ohms? I don't know, that all seems a bit too high. I think I'm gonna remove that component. I'll have to take the heatsink off. Yeah, something seems wrong with this. I had gone over this board and checked for the caps being good, but I didn't check to see if any of the semiconductors were good. I almost feel like the voltage regulator is actually bad, because I don't see how the input, which is a 33 volts, which is not connected to anything else on here, is somehow with like 13 ohms or whatever it was we measured to the middle pin, which is, you know, should be ground, you know, through that thing. I mean, it's not connected to anything else. I mean, there's this little tiny capacitor here. Maybe that cap is shorted. Oh, it's a tantalum cap. That could be our problem right there. I'm going to remove that tantalum cap here, and let's see if that changes the readings. Yeah. Well, it's off enough for me to do testing. Let's get the multimeter over here, and let's check out what we see for those values now. So this is the input here, and let's go to the middle here. Yeah, 17 ohms again. And of course, to the output, remember we had 30? Now we've even less now. What? All right, so it's definitely not that cap. Sorry, I blamed it for something. Well, luckily I have a second one of these boards. I'm gonna go grab it. Let's take a look at the way that one looks. Here it is. This is the one out of the battery damaged Lisa. Hey, this one actually looks in pretty good shape. Well, actually, no, there's corrosion on the backside here, isn't there? But that's the regulator. And there's that little tantalum cap, same one. So let's poke around there and see what we see for resistance values. So that's the input on the regulator, 3 or 4 megohm, and that's to the ground pin, which is the same as the middle here. Yeah, 4 megohm. So yeah, this is going to the heatsink, which is bonded to the actual regulator. And don't worry, this is on an island on both sides, so it's not actually connected to anything, either one of these, but it is connected to the middle pin. And we go to this side, 3 megohms. All right, so that regulator had failed on this one. So that was the main problem. I wonder if that somehow decommissioned this particular Lisa, like the barn find one, which is the one that Jared had, because there's no way this could work, right? So I guess I'm gonna have to swap these over. This one is cleaner, but I don't like this corrosion that's on here. I mean, it's not something I can't clean up, but look, it's on both sides. So for now, I'm gonna try to make this one work by swapping over this regulator. And I don't have any 7824s to try, so I'll have to take this one, and I'll definitely need to test this out of the board, because what if there's some conductivity due to the carbonization of the board happening on there, where that black part is there. So we'll test this once it comes out of the board. All right, there's our regulator. Now, obviously, first thing I need to do is we'll just test the resistance on this out of the board, because like I said, it could be the damage to the PCB itself causing those issues, but we will know in just a moment. 30 ohms and 17 ohms. That is dead. So let me extricate the 7824 off this, stick it on there, and I'll have to replace that burned resistor. Luckily, it's 120 ohms. Pretty simple, and I should have one of those. Yeah, I'm just looking. I could steal it off this, but I'm pretty sure I can find one. Here's our burned resistor. Might actually still work. 56 ohms? Wasn't that supposed to be 120? Let's check it on the other board here. Yeah, 111, 112. I'm just going to pop a 100 ohm resistor. It will be fine because there is that pot that you can adjust the width. If anything, the 100 ohm resistor might make the width narrower or wider. I'm not sure, but the potentiometer's there, so you should be able to dial it in still. Everything has been soldered in again. Let's check some of these resistance values. So from ground to the input, 3.5 megohms or whatever, which is fine. Ground to the output, 1K, but that's probably okay. But the input to the output, 10 megohms. That is correct. It should not be connected together. I think what was happening is this regulator was bad and it was actually sending that 33 volts all the way through into the rest of this. Hopefully that didn't damage anything. I'm glad I had the horizontal output transistor removed, because I think that is hooked up to the 33 volts. Well, sorry, the regulated output of the 33 volts, so the 28 volts or something. It's probably okay because it's close enough, and I have to imagine that whatever was going on with the burning on this board had brought that rail down on the power supply, so it wasn't 50 volts, it was down around 30 volts. Oh, one more thing I gotta fix is I gotta reinstall this little tantalum cap. I almost forgot about that. Let's just check that this cap is not shorted. Yeah, megohm. So I think that's fine. Let's try turning the width control. I don't know, I'll turn it all the way to one side. Let's see what that looks like now. So I was measuring between the ground on the regulator, which are the two lugs here, and the actual ground of the board. There we go, we're like at 3K now. And if we turn width all the way to the other way, that's gonna put all the load, I think, through that little small resistor. So we should be back at 100 ohms or 93. Let's measure what that actual resistor is that I installed. Oh, 95. Okay, so yeah, there we go. All right, so I'm gonna set the width control somewhere in the middle, which is giving us 270-ish ohms. That is the ground reference for the regulator. Okay, I think it's time to test this again and see if I release the magic smoke again and cause that to die as well. I don't think that should be the case. If it were somehow overloaded, I mean, I just don't see how. This can supply, especially with the heatsink, 1.5 amps according to the data sheet, and there's no way that 33 volt rail on the power supply could supply 1.5 amps at 33 volts. That just seems super unlikely to me. So I don't think there's like something else shorted on this board that's somehow causing that regulator to fail. But I guess we'll know shortly, because if we run this again and it becomes a brick just like this one, then There's clearly another fault on here. Let's use this container for holding all of our bad parts so far. So that one and that resistor. Okay, for powering up the board this time, I know this is not ideal because these cables are sort of in the way, but I want to have it where you could see if any magic smoke is released. So it's sitting there just like that. I guess we're going to turn on the system. And what you see below me here is the output from the RGB HDMI. Nothing is touching it. It's definitely floating. And I'm going to turn on the Lisa and we're going to watch that because if anything smoke comes out, I'm going to get my hand on the power switch to turn it off. Here we go. 3, 2, 1. I turned it off because I realized I probably should have got the thermal camera out so we could look at that. Or I could look at that at least so that I could see if it's getting hot and it's going to smoke again. Unfortunately, I don't have a way for you to be able to see the board and the thermal camera all at the same time. So we're going to do it this way. Here we go. 3, 2, 1. Well, that seems normal, doesn't it? And the Lisa's booting, so that's good. There's a lot of glare, unfortunately, on the thermal camera, but the resistor did not get hot. That is great. And the heatsink for the regulator is not hot either. So what I want to try to do is measure some voltages on this board. I want to look at what's going into the regulator and what's coming out of the regulator. I have this clipped onto the input into the CRT board. So this is the unregulated 33 volts. There it is, 37 volts. Okay, 36, that looks good. Turn the power off to the Lisa. Let's let that drop, and then we'll check the output of the regulator. Let's push the power button. 31 volts. Okay, so that's a bit high. Let's turn that width coil. Okay. There we go. 28 is what it said it should be. What we can see here is this regulation circuit is now working properly. So without a doubt, the regulator that was on this board, the one that's in here now, that was bad, and it took out that resistor. Okay, I just turned off the Lisa, and there's that voltage dropping. So there's not as much load on it as there normally would be because the flyback is hooked up to it and some other stuff that is not currently connected to this. But it makes me happy that when this board is connected, just as I suspected, the input voltage is not going to be 50 volts, it's 36 volts, which is completely acceptable. I'm finally confident that the Lisa can run for an extended period of time, and I don't need my electronic load because the CRT board doesn't seem to be letting out any magic smoke. And I think it's time for testing the keyboard and seeing if I can get into service mode. So here's the little Mac 2 Lisa keyboard adapter. This is the connection, this yellow wire that goes to the Lisa, and this is for a Macintosh keyboard. There are versions of this for like PS2, USB, I can't remember what else. Maybe ADB, I think there was as well. This was designed by James Denton. There's his website. You can go pick one up if you need one of these yourself. I went for the version that uses these original Mac keyboards because I think this is the closest fit to what was originally on the Lisa. I don't ever think I'll ever get a real Lisa keyboard, so this should do the trick. Now the wiring harness with the ribbon cable that I made, this goes to the power switch. There's a power LITE that's not working, but we'll get to that. And this connects to this connector like so. Wow, that doesn't really go in very well. Okay, that got stuck immediately. This is probably dirty inside. Let's try to clean that up a little bit. Okay, I'm gonna get some deoxit on a cotton bud. Doesn't really come out that dirty, actually. Now remember that I actually have 2 of these. This one is from Jared, so this is the barn find one. It could be that the other one works better. Might have a working power light as well in the switch. The switch might have a working light. It just could be dirty contacts as well. I'm not quite sure why this wasn't going in very smoothly and easily. There we go. Deoxit definitely helped there. The instructions that came with this was very explicit that you should never plug any of this stuff in while the machine is powered on. So everything is turned off and I don't even have power going to the power supply. At this point, the mouse is plugged into the computer, keyboard's connected. Let's give this a try. I'm afraid every time I go to turn this machine on that something else is going to break. I'm going to let the magic smoke out of the adapter. Okay, anyways, I need to stop worrying and just get on with testing. Here we go. Okay, good. The amber light came on. That was expected. Now, I did a little bit of reading. It said to go into service mode, you push the space bar once it starts the diagnostics. Or not. Okay, let's try booting from the disk. Or actually, let's see if the keyboard's working. Apple II. Oh, that worked. Okay, cool. So the Apple key, there's no Apple key on the actual Macintosh keyboard. The Apple key is the equivalent of the Option key, which happens to be this key right here with the clover leaf. Oh, there it is. It was the Command S key. Oh, yes. Awesome. Power cycle, adjust video. Ooh, look at that. Oh, this is cool. So that should work from the keyboard as well. It does. So display memory, that's obviously going to display the RAM in this service mode window. Address, I don't know, 1, 2, 3, 4. Count, 100. There it is. Nice. Now what I'm curious about, when I hit display memory, so these are the numbers. Let's just see if everything is working. Can I type letters in here? Oh, I can. All right, so it definitely appears that this keyboard adapter is working perfectly, and that means whatever's handling the keyboard, whichever chip on the board, is working as well. So that's GPIO lines on probably one of the 6526s. In fact, it's the middle 6522 that is handling the keyboard. It says keyboard right on it. That's actually kind of cool, because what I should do is swap the two 6522s just to make sure that the disk error I'm getting is not caused by the other 6522. I'm not even sure that they're in play for the entire disk controller routine, but both of these 6522s came off the battery damaged board, so one of them could be faulty. So I'm just going to turn off the computer. Let's do power cycle, which I assume turns the machine off. Power cycling at 60. Oh, okay, this will just turn the machine off and on, I guess. Okay, not particularly useful. Ooh, look at those little pixels there. This could be something on the RGB to HDMI. Before I jump to any RAM problems, let's do the auto calibration just to make sure. Yeah, I was worried for a second that the RAM was going bad because the video image we're looking at is stored in the main memory. And those little pixels that were moving up and down, I thought, uh-oh, but that was just a sampling problem with the RGB HDMI. No problem. Okay, cool. I'm going to turn the machine off, and I'll spend a second to just swap around those two 6526s. The one that's not in the keyboard slot, it says parallel port, it had some corroded pins that I dremeled. The one in the middle slot, which says keyboard, doesn't. So I just want to make sure that they're both actually working. Okay, those are both swapped around. One thing to consider is the sockets that these are in are the original 1983, potentially single wipe sockets that were on this I/O board that I got from Jared. So it's possible it might not be making good contact. So before I condemn that chip, if it doesn't work, it might be just works anyways, I may need to change those sockets. There is deoxit in those sockets, so that gives them the best chance of actually working. All right, here we go. So again, this long reset here where it's just black, that's a problem on the CPU board that I'll have to address. Okay, keyboard still works. That's cool. I was typing stuff on here. Okay, cool. I take it we still had the error, right? Let's restart and let it run the diagnostics again. I'm assuming we had the error 57. I didn't even notice. I was just trying to get into the diagnostics immediately. Okay, so perfect. Because it is now time to take a look at the Troubleshooting Self-Error Test number 57, written by Sigma 7. The article starts by saying that for the Rev H boot ROM, which happens to be what's in this machine, this error 57 equals eDisk, which basically is disk error disk probably. And looking at the code for eDisk, we find it at address 1152. That's the offset 1152 from the start of the ROM. There are three possibilities for where the error might be generated or detected. The ROM version display and timing of the error message help narrow down what is happening. 1186, this is an offset in the ROM, the IO ROM version displayed on the screen by the code at 111A, which writes the slash character after the CPU board ROM version, e.g. H, and then reads the IO ROM version from the FDC shared RAM. Floppy drive controller has some RAM, 2114 shared RAM. It reads that version from there and writes it to screen. If the attempt to get the IO ROM version fails with a bus error, execution will redirect to something else, and nothing will be displayed after the slash. Well, here is our boot screen. Up at the top, H That's the main ROM version on the CPU card. And then there's the slash, and then we have an 88, which is the IO ROM version. That's for the floppy drive controller. Well, I had done a little bit of searching and I found this webpage, LISAFAC, and it has known IO board ROM versions. Well, A8 is the original Lisa 2 ROM that would have been on the machine that was battery damaged, but 88, that is the version that's on the 2/10, and that is exactly what I put on the EEPROM. So I flashed this EEPROM 341.026.1D, and that's what's in this board right now, and that is what is showing up. So that tells us the diagnostic routine is able to communicate with the shared RAM and read that version number out of it. So this article goes on to sort of talk about what you can do to test the shared RAM and stuff like that, or access it, but obviously it's able to be accessed. So the next code in the ROM, after displaying the IO ROM version, the self-check or self-test checks to see if the floppy drive controller has asserted the disk diag, which is U3E-11, which is done after the 6504 successfully goes through its reset sequence. Disk diag U3E11, we got to look up what chip that is, on the schematic is controlled by the 6504 with writes that equate boot L and boot high in the IO ROM listing. Disk diag is set low by reset, and the 6502 writes to boot H, setting the disk diag high when ready to interact with the 68000 chip. But if the floppy drive controller is working or semi-working, you should be able to see the state of the signal be low upon reset and then go high shortly after. And if it's stuck low, then the 6502 or 6504 circuitry may have some kind of problem. The boot ROM listing suggests the 68000 waits 15 seconds for disk diag to go high. So if the amount of time between seeing the IO ROM version and the error appearing is much less, the error is likely 14C6, the next chunk, because the error appears instantly, not 15 seconds. Now, apparently, we should be able to see this line toggling, U3E pin 11. Okay, so the multimeter is hooked up to that pin 11. It's currently just sitting at 0.22 volts. The system is off. Let's turn it on. Okay, it's at 0.3 volts. That's that disk diag signal that should go high during the diagnostics process. Oh, there goes high. Okay, so that is the 6504 CPU setting that value high. So to confirm, it's definitely not that part of the routine that's causing the failure, it's the next part. Okay, so after finding the disk diag high, that's that signal we confirmed goes high, the 68000 checks the startup status of the floppy drive controller as stored at this memory location, and it needs to be 00. Attempts to write 55 and read it back from this floppy drive shared RAM, and issues disable interrupt command to the floppy drive controller. If any of these fail, error 57 is generated. The startup status retrieved from FCC017 will not be 00 if the FDC detected an error upon reset. See error numbers extracted from the IO ROM listing below. There are the error numbers. Let's take a look at that value. If the keyboard is working, one can use service mode to check these manually to see which one is failing. 1 FCC0171, read one word from FCC017. The status byte with the error code is will be returned. Cool. And these are all our various errors, I guess. Invalid command, drive number, blah, blah, blah. Okay. We are going to look for address FCC017. And I guess I could just push space 1. And there is our, I guess, word. So I called for FCC017, but I got back 016 because this is a 32-bit processor internally. One thing that's odd is every time I read this value, let me point at this, I have a mouse to do that. Well, this value 10 is not changed, but all this other stuff is kind of changing. And I don't know if that's on purpose or if that is a problem. That could easily indicate that the shared RAM we're using here, I don't know how it's hooked up, we have to look at the schematics, has some bad bits. Although 00, FF, AA, I mean, that's changing dramatically. So that would indicate that all the bits going to the shared RAM are bad, but the 10 never fluctuates, these zeros are solid, those zeros are solid, so certain values never change. D5 also never changes, A7. So what I'm a little confused is actually I'm not 100% sure which byte is the relevant one. Is it the 10? It's obviously not the first one, because I think that would be That would be 16. Is that 17, 18? The article doesn't really document exactly how the shared memory maps into the Lisa address space for the 68,000. Now, further down the article, it talks about writing to the memory and then reading the value back. If service mode is available, one can test shared RAM manually via reads and writes to odd addresses from FCC001 to FCC1FF. The end of this range is used for Lisa parameter RAM and 6504 stack, and the beginning of the range is used for floppy drive operations, values, commands, etc. So random writes using the middle of the range is less likely to cause any hiccups. All right, so it's saying between 001 and 1FF. Let's just try FCC 100, and let's write some values in there and read it all back and see what we get. And it's saying, by the way, that it's odd addresses that we can write to. I guess that's the way the 68,000 maps to the 6502 address space, or RAM, I guess. So I did set memory, and we're going to write to 101, and I'm going to try writing AB to it. And when we read this again, there's an AB. I guess I thought it would be over here, but the reality is it's there. Let's do that again. Set memory. Let's try this again. FCC 101, and we'll write CD, and we'll read this back. All right, there it is, CD. So it is working. It's definitely able to write to RAM what seems proper, at least in this particular spot. And now that helps me understand where these values are. In fact, that tells me right here that error 10, that's the error. Because remember, the error was at FCC 017, and we know that 16 is the AA or 00, and these are just junk bytes. It's these odd addresses, which when we go down to the list of errors, error 10 is invalid format parameter. What? That doesn't make sense. If we saw some of this other stuff like random IRQ or ROM test failed, I mean, I could believe that stuff, or I guess drive error or error stat, write protect, I don't know, this stuff. That doesn't make sense. It looks like these error numbers, by the way, are all for like when the floppy drive is operating and say the operating system queries the controller to figure out, why the disk operation didn't complete. Stuff like, track number is wrong, or the disk has a problem, or couldn't verify, or whatever. So I'm not quite sure what would cause this error 10 to appear at this point in the boot process. And I imagine on reset, it should be 00. I wonder if I should just reset the 6502 or the 6504 processor so it just restarts. And then we can take a look at that memory location to see if we have that 10 again. Maybe it'll be 0 at that point. Okay, I'm going to take a quick interlude here, and I'm just going to cut these wires off this speaker, which I really feel like this speaker might be bad. And I clipped the output to this speaker here. I measured the voice coil on the speaker, and it is 8 ohms or 7.8, but it's quite possible it can't move. And that's why it doesn't beep. So let's see what happens with this one, if anything. No, it's behaving exactly the same as the other one. There's a little bit of hiss out of it, but when I went to go beep there, after the diagnostics failed, I heard like a boop, boop, boop kind of sound, but very, very quiet. And yeah, it's obviously something wrong with the amplification circuit on the Lisa. So because there's a problem, I'll just unplug this, that way I don't short it out or whatever. Well, anyways, on reboot, let's display FCC 0, what was it, 16? Well, it's 17, and 1 byte. And yep, there it is. We're getting a 10. That same 10 is there. The funny thing is here is that if I quit and we do startup and we do the internal floppy drive, part of me wonders is if it's trying to currently talk to the floppy drive. And once this is done, if we can go back into service mode, maybe I can look at that memory address again. Okay. Yeah, we can still do this. Let's display memory again. FCC 017. No, it's still a 10. I was just thinking that maybe it was able to like talk to the disk drive. Well, there's no floppy drive actually connected, but maybe it was actually trying to boot from it. And maybe it would have changed the code that's in here. Instead of a 10, it would have been something else. Now, I was thinking about maybe trying to force reset the CPU, the 6504 on the disk controller. And I wanted to see where the reset line actually comes from. Looks like, okay, it's hooked up to the integrated WAS machine as well. I don't actually know if the IWM chip is working because I took it off a battery damaged Mac SE. So the LS259, that's the chip, what was it, pin 11? Yeah, disk diag, that's what the CPU is looking at. That is working. And this chip does reset its output when the LISA resets. So when you reset the LISA through this signal, then disk diag will go low, along with all the other outputs. So the reset signal, though, looks like it comes from J123. I think that's the main connector that goes down to the motherboard. Pin 23, there it is, reset. So that goes to a bunch of different stuff on the I/O board, and that's obviously coming from the CPU board itself. And what's funny is the reset button doesn't work. Now, that could easily be my fault. I didn't hook it up correctly. But I wonder if I should just try one of the spare CPU cards, because I have another one that Jared sent me. We should just try that, see if the reset behaves differently, like the system powers up much more quickly. And maybe the reset button starts working, and maybe the disk controller starts working. I don't know. I'm kind of grasping at straws here a little bit, because definitely there's something wrong with the reset circuit on this CPU board. This is the battery damaged one. Okay, so this is the CPU board that Jared sent me. It's in really good shape, except it's got corrosion right in the middle here that I didn't attempt to clean up. That looks like it came from a critter that was living inside the computer or something like that. Let's give this a try. It's got the H ROMs, by the way, so same exact ROM version as what we were just trying. What I should do is at least clean the edge connector first. Right, the CPU board is in. Let's see what happens now. Okay, here we go. I'm going to hit the power button. Well, that's a good sign. Black screen, except, I mean, it's supposed to be fast, Alex told me. It's not supposed to take this long. Oh, it's like the other one would have had to display by now, wouldn't it? Okay, so this CPU board doesn't work at all. I suppose that means future CPU board repair. I'm not 100% sure how to accomplish that, because it has to go into the card cage. And when it's in the card cage, you can't access the board. I just put a little deoxit on the edge connector, and I have some magic eraser here. I'm just going to give it a little bit of a clean. There's already deoxit in the socket because I had deoxit on the other board on its edge connector, but I think a little bit of deoxit on this one can't hurt. Okay, it's back in. Okay, let's give that a try again. I mean, the black screen is coming from the CPU board. Yeah, it's still not working. One last thing I'm going to try, I'm just going to reseat the socketed chips. All right, CPU, 2 ROM chips, and the PROM all got some deoxit, and I reseated them. Push the power button. No. Definitely we have a faulty CPU board. Amazing that the battery damaged one just worked, but this one, it doesn't work. Wow. Incidentally, there's the 555 timer, so probably this cap and these resistors and whatnot probably form what generates the reset circuit. Which on this board, everything looks good in this area, but we know that it's very slow to come out of reset for some reason, which I'm assuming is some value here is drifted or something like that. Here's the reset circuit. There's the 556 timer. There's the reset switch input, pin 6. Looks like the main timing capacitor is C8. That is electrolytic, 2.2 microfarad through a 470k ohm resistor to 5 volts. So that's C8, the silver package, and R2 is that resistor there, 470k. So the cap should be 2.2 microfarad. It says 11. So that's probably why it's so slow. Let's take a look at the other CPU board. It's labeled as 2.2 microfarad. I can't read the other one. The label's on the bottom side. Yeah, 2.8 microfarad. So that's at least correct. I mean, the fact this one is so slow to start, I'm going to replace this cap. Well, at least put in 2.2. Okay, the cap that I just took out is 10 microfarads. Okay. Right, I know it's not super pretty, but all I had was a radial cap. I put it in that correct spot. Now, the funny thing is that the reset switch actually is affected by this cap. So it's possible that, I bet the reset switch has a resistor in between it and this pin, and it's possible with that 10 microfarad that reset switch maybe wasn't effective. I don't know. We'll find out. I might still have the reset switch on the wrong pin on the motherboard. Let's hit the power switch, see what happens. So this is, oh yeah, look at that, fast. I doubt this is going to fix the problem with the I/O board and the floppy controller. I'm sure this is still going to give us the same error. But that is as fast as I remember Yeah, 57. Okay, let's try hitting the reset button now. Nope, that doesn't do anything. I must have it on the wrong pin. That's got to be the problem. Or not. Wait a second, what? It rebooted. Do you have to? Oh, no, it's working. The button works now. It just doesn't work instantly. You got to hold it for a second. I suppose that's probably a feature. So I hold it, and when I let go, okay, yeah, it's working. So I guess with the old cap on there, you just have to hold it for a much longer period of time. I'm going to hold it down for 1 second and let go. And it works. Okay. All right. Fixed 2 problems. Actually fixed 2 freaking problems. And the weird thing is that slowness would have been like this from the very start. So I don't know if like early boards had this and later ones didn't, but all of Alex's CPU boards that he tested started up immediately, didn't have that slow startup. So that 10 microfarad cap, which was definitely original because it matches the other ones on the board, I just don't know what's going on with that. But anyways, with the new one in there, it reboots quickly, and now the reset switch works. So at least that's fixed. Well, as you could probably tell by my clothing, it's the next day, and I've had some time to kind of think about the disk error and maybe some causes for it. Now, there's a few things. When I first was talking about the error, once I figured out that it was error code 10 by looking at the memory, I was going back to the list on that article posting, and I thought, oh, it doesn't make sense, the error we're getting, error 10. Well, I had a little bit of brain fade, and I'm sure lots of people notice this and were screaming at their screen. It should have been obvious to me that this list, because it starts at 01 and it goes to 31, is in decimal. And obviously when I'm reading the error code out of memory, those are hexadecimal values. And it was actually Alex the cat who pointed this out to me because I sent him a message just asking what he thinks about this error code that didn't really make sense. Invalid format parameter. And Alex was like, you know, the list is in decimal and what you read out of memory is hexadecimal. And I was like, oh, duh, of course. Total rookie mistake there. And it even says that somewhere in here. Note the pic shows decimal, not hexadecimal, used in service mode. So hexadecimal 10, like we saw in the service mode, is not invalid format parameter, but this one, value 16, drive error unable to leave track 0 location. Now you might be thinking, okay, well, it's trying to move the heads or sense that it's at track 0 and it's unable to do that because the drive is just not connected. But everything I have read, including what Alex tells me, is that the disk drive does not need to be connected to the system for the system to pass all of its diagnostics. So that kind of implies there's something going on with the circuitry where it thinks the drive is connected and it's trying to access it. And when I think about this, I've seen this on a Macintosh before, and I don't remember the exact circumstances, but when I had the floppy drive disconnected, instead of it just sort of booting the SCSI hard drive and loading the OS, I would get a disk drive icon with an X through it, which was odd. That's normally if you have a bad disk. I didn't even have a drive connected, and that was happening. And that motherboard had a fault, and I don't remember if I fixed it or what, but it seems like something similar is going on with this system. So let's go take a look at the schematics and look at exactly what signals go in and out of the drive circuitry so we can try to figure out why it's thinking there's a drive there and it's not able to seek to track 0. So this schematic, even though it says Lisa 1 IO, is actually for the 2/10. That's the board we have. And we got to look at this one versus Alex's recreated IO board schematics because those are for the 2.5 unit, which doesn't have the IWM chip on it. Here's sheet 4. This has the CPU, the 6504. There's our EEPROM. And over on the right, that's the IWM or integrated WAS machine. There's one thing, by the way, that I have to just mention. This machine calls for the part number for the IWM to be 344-0041, just looking at the board and the actual silkscreen markings. The chip I actually have in here, though, is a 344-0043. The difference between the 41 and the 43? I don't know. Can't really find any info online. I saw a few posts of people thinking that they were maybe interchangeable, but not 100% sure. The 43 specifically comes out of the Mac SE and probably the Classic and later models, while the 41 is used on the Mac 128, Mac 512, also the Apple Lisa, this version at least, and on the Apple IIc. And I think the Apple II Smart Port cards also use the 0041. I've always had a hunch that the chips were all interchangeable. And I kind of recall someone saying they used this 43 chip from an SE on an Apple IIc, and that worked fine. But maybe the Lisa is more picky. So if what we're looking at here with the schematics don't really lead anywhere, then perhaps that's the problem. And I'm gonna have to go find another chip, maybe steal it from Apple IIc to test on here to see if that's the problem. Although when we take a look at these error lists, one of them is error 14, fatal error, IWM doesn't respond to commands. So it almost feels like if it was unhappy with the IWM, we would get error 14 as opposed to error 16. Let's take a look at the IWM and just take a look at what things are going in and out of it. I'm more familiar with like PC floppy drive interfaces and the SugarArt stuff, not so much the way the Apples work. Okay, so outputs, we have P0 through P3. Obviously, those are buffered, and those go to the phases. This actually is for the stepper motor control on both the 3.5-inch drives and 5.25-inch drives. We have what looks like the write request line. That's RWQ. We have E1 and E2, drive 0, drive 1. That's going to be the drive select lines that turn on the disk drive. There's an HDS signal, which is actually coming from the LS259, same place that disk diag signal is coming from, which we know works. That is controlled from the CPU itself. That would probably be head select to select which head is being used. And you might be asking, why does it have head select when it's a 400K disk drive on the Lisa, which is only single-sided, it's only one head? Well, it's because the Twiggy drive used on the original Lisa had two heads. It was a 5.25-inch drive. It had two different read-write heads. Instead of being on top of each other like on a normal double-sided drive, they were actually offset from each other. And I don't know if they both read the same side or the other side, but either way, that head select signal almost certainly is to select which heads be used on the Twiggy. And theoretically, it would mean that we could use an 800K floppy drive on here as well, 3.5-inch that is, and it might be able to use it. Maybe not Lisa OS, but the Macintosh XL OS probably could. Also down here on the LS259, that's from the CPU itself, motor 1 and motor 2. So that's probably not drive select, but like motor on signals for the floppy drives. There's also the stop signal, which I'm not sure what that's used for. It looks like it doesn't go to the main connector. Anything that's labeled J1 goes to the actual connector down to the motherboard. That is going to another sheet 5, some component. So there must be some more logic along with motor 1. Possibly this is used to maybe in combination with these other signals like the drive select and the motor signals to eject the disk drive. I don't know exactly how Apple drives do that eject thing, but there's clearly a way. Now, moving back up to the top where the signals that go into the IWM, we have this SNS, which probably stands for sense. Yeah, because it says sense right there on pin 21. And you know that's an input into the chip because we have these logic gates that are facing, the output side of the logic gates is facing the chip. So that's obviously an input. Write data, that's an output. So that's the data that comes out of the IWM to be written to the disk. And then we have read data, which comes in, that goes into the IWM through a buffer. And then we have some signal that's an input called twig, and that goes through an LS04, and it goes through this other gate on the LS38, and it goes down into the sense signal. So the sense signal is made up of 3 signals: read signal, the sense signal, wherever that comes from, and this twig signal. All this stuff is gated together into that sense pin. Now you have to be asking, what is this twig signal? Because the Lisa 210, which this I/O board is, was never designed to have a Twiggy. It was always going to have a 3.5-inch floppy. So what is this? Well, Alex told me that it seems that Apple had designed provisions with this I/O board to actually support the Twiggy. And it might have been because maybe someone might have had to replace their original I/O board in their Lisa 1 with the Twiggy drives with one of these boards. And maybe that signal is used somehow. And if we take a look at that Twiggy signal, it also splits off. Now it goes to address line 12 on the EEPROM. And if you recall, when I installed the EEPROM in this machine, I used a 2764 as opposed to a 2732. And the only difference between those two chips really is it has an extra address line 12. Well, to make sure that the ROM was always selecting the correct ROM image, the one for, well, this system, the DROM, I put a resistor between A12 and ground. Now, I think I used a 4.7K resistor because I didn't know for sure if this was actually hooked up to anything. I didn't look at this schematic. I just assumed it wasn't because I was checking it for being grounded or being pulled to 5 volts, and I didn't see either. But my presumption here is that this Twiggy signal, which is normally just pulled up to 5 volts through a resistor pack, it goes through this LS04, and that is able to select which ROM image you have in operation. So I guess the version of this I/O board that supports Twiggy drives probably had two different ROM images on a 2764, with the lower one, the first one, being for normal 3.5-inch floppy drives, and the other ROM reprogramming this and using the IWM to control Twiggy drives. And that would select which ROM image is being used. Is it somehow possible that my resistor that pulls A12 down to ground is causing an issue? I don't think so, because when we take a look at the LS04, that should be driving the signal either to ground or to 5 volts, depending on what its input is, and that should override that 4.7K resistor that I have on the EEPROM, which theoretically could backfeed into this LS38 and maybe affect this sense pin. So I suppose if this LS04 driver is somehow bad, like maybe it's not driving the signal at all, maybe there's a bad trace, for instance. Now that doesn't make sense, because if we look at what's happening here, the input to the LS04 is pulled up to 5 volts by this pull-up resistor pack. So that means that with no Twiggy signal, that should always just be at 5 volts. And this is an inverting gate. It's got a little circle there next to the 2. That means that when 5 volts is going into it, it should be ground coming out of it. Well, that would drive my address line 12 to ground, but I just happen to have an extra resistor on it anyways. And therefore, the LS38 pin 9 input should always just be grounded, and then whatever the rest of the logic is through all these other gates should give the sense pin exactly what it needs to know. And I'm presuming between the read signal and the sense pin, it can tell the drive is there or not there, for instance. Now let's just think for a second what these signals should look like when the disk drive is not connected. So this read signal is going to be pulled up to 5 volts. That gets buffered but not inverted. It goes to read just as 5 volts. And then the sense signal is pulled down with a 1K resistor down to ground. So that's pin 5. That gets inverted, so that becomes high, 5 volts. It goes into this LS00, which is a NAND gate. So what NAND gates do is if input 1 and input 2 are both 5 volts, that satisfies the gate, so it becomes true, which would normally be logic high, but then it's inverted because there's a circle, so it becomes logic low. So generally in the idle state, I think the sense line should just be low on pin 21 on the IWM. And if you're wondering about this LS38 and the fact that it's got a pull-up resistor, and you're like, how is that happening? That's because this LS38 is actually an open collector driver. That means that this cannot pull the signal up to 5 volts. It can only pull it down to ground. And it has the same symbol as this one, so it's a NAND gate as well, but it needs a pull-up resistor to actually have a high signal. So in the default configuration, if we look at this NAND gate, then basically this is 5 volts, it gets buffered, doesn't get inverted, so 5 volts or high is going into pin 10. And then the Twiggy signal, which is going to be 5 volts if nothing's plugged in, which I assume nothing is going to be plugged in, is going to turn into a 0 or a low signal, which goes into this. That means that this NAND gate is not satisfied because it doesn't have 2 high inputs. So that means its output is going to be low, but that's inverted, so that turns to high, which it can't drive high, so it's going to be using this pull-up resistor. Yeah, and that means that essentially 21 should be low in the default state where no floppy drive is connected. So I think what I need to do is power up the Lisa, take a look at this pin 21 on the IWM, let's see what that is, and let's see if it's high. And if it is, we need to analyze these logic gates to figure out what's pulling it high, like what signal is causing it to go high. I still don't think it's going to be my pull down resistor on address line 12. I'm positive it's not going to be that. Maybe I pulled it to 5 volts. No, I didn't. I definitely pulled it down to ground with like a 4.7K. So the multimeter here is connected to pin 21, the sense input on the IWM. Let's turn on the power to the whole system and push the power button. Okay, it's low. And absolutely the system booted up and gave us that error. And the whole time the signal was low, which is exactly what I expected it to be. Right, let's take a look at the output of the LS04. I just want to make sure to see if that ILI is down around 0 volts, probably like 0.3 volts or whatever, because that should be what's happening, because definitely 5 volts is going in when nothing's hooked up, and that should invert that and become ground, and that also drives A12. So this is now hooked up to that pin. Let's turn the system on. Yeah, okay. So I don't need that resistor on the back of the EEPROM. This is definitely going to keep that EEPROM running on the first half of the image on the 2764, but the resistor is not really doing anything, so it's fine that it's there. But that just validates that that is not the problem. Absolutely, definitely not. So I guess now I'm a little bit stumped because I don't know if the problem is maybe the IWM itself is just not compatible. Perhaps the way that sense line works is different on the 43 versus the 41. because frankly, that's the only signal that really makes sense for what we're seeing. I suppose I should look at the read input signal, because that's the only other input signal there is. And we should make sure that that is up at 5 volt, because based on what we see here, read comes in, pull up resistor, there's a non-inverting gate, and that goes to pin 22, and that should be up at 5 volts. Let's make sure that that's also 5 volts, because maybe it's somehow using that to determine, whether the drive is there or not. So what we're looking at here, and the system is off, that is pin 22 on the IWM, the read signal. Let's turn it on. Yeah, and it's low. That's exactly what we would assume it would be based on the schematic. So there's no smoking gun, unfortunately. I was hoping that I'd be able to figure it out, and maybe it was that resistor or something like that, or some logic problem here. But the inputs to the IWM, they all look proper. And that's it. Those are the only inputs into this chip. Everything else, at least when it comes to the floppy drive signaling, is an output. So therefore, it should not be affecting what the diagnostics result in, because all of this is an output. Nothing is an input at all. So it kind of leads me to think that this is an incompatibility with the 0043 IWM chip. And I need to find a 41 and try that in this board, and that could be our entire problem here. Right, this is an Apple II 3.5-inch disc controller card, also known as the LITE. It's basically a disc controller that has an integrated WAS machine chip on it. Happens to be a 3440041, so the one that Lisa uses. It was soldered, but I added a socket. And this was the one that was on the Lisa that I took from a Mac SE, 3440043-A. Let me pop this 41 into the machine, see if this fixes the problem. Right, power up the machine. Look at that nice quick booting, thanks to swapping out that capacitor on the CPU board. Okay, same exact error. So if we go to service mode and we take a look at the memory, FCC, I think it was what, 41? That's not the right location. It was FCC 017. Nope, error 10. It's exactly the same error we had before right there. So no difference whatsoever with this chip. Okay, well that's cool, because I wanted to put this Mac SE one back on there, and if this one works, then great. But of course, nothing's working yet, so I have to poke around a little bit more. So part of me has me wondering, if we take a look at the disk controller section, maybe one of these signals is in a state that makes it unhappy. Like maybe the sense line needs to be high, for instance, when the system is idle. I know based on the way these pull-up resistors and pull-down resistors are, the way it is now where it's low going into pin 21 is correct based on this logic. But maybe just as an attempt to try other things, I could try pulling this up to 5 volts, pin 5 going into this gate, or I could try pulling down pin 1 going into that gate. Those are the same chip, incidentally. I don't know if it's going to fix it, but maybe it will change what we're getting. I'm sort of grasping at straws here, because I just don't have an idea of like what exactly is going on here. Right, so I just clipped onto pin 5 of this LS04 U3F, and I have it clipped onto 5 volts. So that's going to override this pull down resistor. It's going to make this sense line essentially go high. So we'll change what the IWM sees. Okay, here we go. Let's turn the system on. It just passed the diagnostics. It just freaking passed the diagnostics. So if we go to service mode, which is interesting, it doesn't go into service mode. I guess I'll push the reset button. I assume service mode, you have to initiate it while it's running the test. Okay, I don't even know how to get into service mode. Do we try to boot? It says insert a disk. So it knows there's no disk. That's different than it ever did before. There we go, I could go to service mode there. FCC 17, there it is, 0. So that's the problem, is not having the drive connected makes the computer think that there's a disk in the drive. Of course, it's not going to be able to control a drive that's not there. You gotta be kidding me. Let's reset that again and see what it does. I mean, it's going to work, right? Wow. So again, no error, and we do 2, and it says insert the disk. Now my assumption is if I unplug the 5-volt line that's on that pin of that gate that it's going to think a disk is inserted in the drive. I'm going to do that while the system is running here, just very carefully. Okay, I did do it. I'm going to do startup from again, and I'm going to pick a disk. And look, see, it's not saying insert disk now. It's just trying to load a disk that doesn't exist. And of course, if we go to service mode, once this finishes, there's the error. It's going to have that same error, FCC 017. It's going to have a 10. There it is. There's our 10. So one thing I don't know for sure is if this disk drive subsystem does work. I guess it's time to plug a floppy drive into this thing and see if I can like try to read a disk. I don't have at least a floppy drive handy or a floppy disk handy, but I think I could make one, I suppose. Let's just quickly take a look to see where this sense signal is going. J11, pin 11, that's the connector. And if we take a look at the motherboard schematics, that is pin 11 right there, sense, SNS. I have a feeling that just is going to both of the floppy drive cables. And yep, there it is. So this is the floppy connector, well, the edge connector that goes to the floppy and the keyboard and the power switch. There is the sense signal, and there it is for the other drive. So it's there twice, which makes sense because you could plug in the first or second drive. Now this is the floppy drive cage for the Lisa. And currently it has just the single 400K full height floppy drive, well, full height as in 3.5-inch full height drives. And it's plugged into the little adapter board that allows it to convert from the Twiggy signaling over to what these floppy drives use. And as far as I'm aware, this is the same floppy drive as in the original Mac 128 and the Mac 512. This one looks really, really gummed up. So I actually have no idea if this drive even works without being fully disassembled and lubricated. But I don't see why I couldn't just plug in a normal Macintosh floppy drive. I have several 800K drives, and all of those should work theoretically on this thing. So I think the first thing I need to do is I'm just going to disassemble this and take the interposer off, and I'm not going to try to use this floppy drive. I'll try to use a different one, but let me get this interposer off and let's take a closer look at it. Here's that little interposer board, and yes, the corrosion did make its way onto this board, so I don't actually know if this board is going to work. I did clean up the connector a little bit. It was all green and crusty, but I see there's still corrosion on the backside. The traces don't look damaged, so there's a good chance that this should hopefully actually work. And from my understanding, what this does is generates the variable speed PWM signals for the Apple 3.5-inch floppy drives. Yes, Apple does use variable speed for the spindle motor, and I think that is generated by this board. It, of course, also adapts from the 26-pin connector that was used on the Twiggy drives down to the smaller connector used for the Apple 3.5-inch floppy drives. Okay, with the ribbon cable plugged in, since I made these cables, I'm not 100% sure that they're done correctly, so I need to check for continuity for ground and 5 volts to this board, which should be easy enough. So the negative on this cap is over on this side. There we go, we have continuity. And I just clipped onto the positive side, and I'm going to take this lead and plug this into here, which happens to be a 5 volts. That's what I was using to pull that line high. And yep, that looks good. Okay, good. That confirms that this cable is at least wired up where the 5 volts is correct. So it's not going to damage any of these chips. Well, I suppose the first thing we could do is just try this like that, plugged in without the floppy drive connected, and let's see if that error goes away. And I've removed all the clip leads and jumper leads that I had on the board, so everything is just stock right now. All right, let's turn the system on. See what happens. It's so funny. If this was the problem the whole time and I spent all this time troubleshooting, when the reality was you just have to have floppy drive connected to the Lisa or this I/O board. Yeah, no error. No freaking error. Oh. And look, insert disk. I mean, I can't decide if I want to laugh or I want to cry. Okay, here's an 800K disk drive. I don't know 100% if this works, but at least the disk goes in properly. I have several of these, but I just tried a few of them and none of them are working. Like, they're all gummed up. There is lithium grease on this one, so that's why it seems to work well. Now, what I haven't done yet, obviously, is modify this little LITE adapter board for the PWM signals, but I'm curious to kind of give this a try and see what happens. I don't think it's necessarily going to work without the modification, but at least we should be able to see if the drive spins. Maybe it ejects the disk if you can't, read it, because it's not going to work. This isn't even a valid disk. It's just some random junk disk I had sitting around. Okay, well, let's see what happens like this, and then we'll go from there. There we go. They see that it went to track 0. That might just be what happens with these drives when they're powered up. First of all, let's see if it can detect or passes the diagnostics. It does, right? So we'll do startup from disk. Okay, it's telling us to insert one. So we'll pop that in. It just did something. I didn't even push anything on the key, but look, it's trying to read the disk. Now, I don't actually know if the Lisa has a way to eject disks. It obviously does, right? It must be able to. I'm surprised it didn't eject it, though. Could be because this adapter hasn't been modified yet. That could be the problem. It's obviously seeing the disk there. You see the heads moving. Unbelievable. So if I pop this disk out manually, and now we do continue, it just says insert disk. And if I pop the disk in, it started to read it. It doesn't recognize it in the boot ROM, but that's probably the disk controller CPU detecting that the disk got inserted. So right now on first appearance, it appears that all the troubleshooting I was doing was literally because the drive adapter wasn't plugged in. All of that. So if anyone's watching who's a Lisa expert and you know these machines like the back of your hand, is this normal? Or does the Lisa 210 IO board mixed with the 2.5 motherboard result in you needing to have at least the LITE adapter connected to actually get to pass diagnostics? Because that seems to be what's happening here. Over on Lisa FAQ, we have information on what modifications to make. So we need to cut the trace there on the top side. On the solder side, cut the trace between pins 14 and 20. And then we need to add, it looks like 2 pieces of jumper wire. So from there to there, and there to there. Okay, simple enough. Let me do those mods. All right, there are the modifications. So that trace is cut. And we flip this over. Bodge wire, and one more cut trace. So let's see if this works. Incidentally, we're still running with the 0041 IWM. I'm going to switch this back if this drive does work now. All right, what you could just see is I have my Macintosh Classic over here, the green Apple, and I'm making some disks. I'm using disk copy 42, which seems to be what the Lisa disk images are that I found on the internet. Sometimes, unfortunately, that's really the best way to try to make disks is using a Macintosh. I know the disk drive is working on that Mac, so I'm going to pop the Lisa OS or Lisa Office System 1 disk 1, in the drive. Okay, and what's really curious, if this is still recording, is I plugged the power cable into the Lisa and it tripped my breaker, the GFCI or the RCD. Yeah, that was curious, very curious. So it means there's a ground fault, I guess, inside the power supply. Usually that would come from, say, a REFA cap or potentially an inappropriate cap being in place of a Y cap. That's a safety cap. Typical. So this might be a common problem that I'm gonna have to go into this power supply and remove that bad offending cap that's causing this. But I'm gonna try this again. Let's see if it trips the breaker or not. I have a feeling I'm gonna have to solve this issue, but I don't wanna solve it now. I wanna test the floppy drive. So let's make sure everything is not touching. Okay, here we go. I'm gonna turn on the power strip. Okay, it's plugged in and nothing tripped. All right, here we go. So I think what's in here is Lisa OS disk 1. Let's see what happens. Is this gonna work? Oh yes, it's totally booting. It is totally booting. So there was nothing wrong with the disk controller on this computer at all, nothing. I can't even believe it. Look at this, it's working. Wow. So obviously you can use 800K Macintosh disk drives. I'm sure a 1.4 meg drive would almost certainly work as well. And these are single-sided disks, 400K, which is what's actually loading. Wow. I'm still in shock a little bit. That, look at that, it's like round corners. I'm still in shock a little bit that everything I read said that what I was told is that you don't need to have the drive connected to pass the power on diagnostics, when obviously that information was not quite accurate, at least for this particular setup. So this is obviously working. Look at that. Oh no, oh, well, internal disk. The problem may have been the disk drive was not ready when Office System 1 was started. Try starting again from Office System 1 diskette. The Lisa will restart. Remember to tell the Lisa to start up from the Sony again. The Sony. That they made the original disk drive. You should hold down the Apple key and the 2 on the main keyboard, not the 2 on the numeric keypad while Lisa's performing the self-test routine. If the Lisa continues to have a problem with the internal drive, call a qualified service representative. So it's talking about the widget internal hard drive that existed on the 210, which clearly doesn't work. So this version of Lisa OS or Lisa Office Works or whatever this is called is able to detect that this is a Lisa 210 and is looking for that hard drive, which doesn't exist. I feel if I just plug in my profile externally, it's going to have the same ID. It's going to look like it's on parallel port 1 or even the profile emulator. And then this is going to actually work. All right, let's get the mouse over here. Look at that mouse pointer. It's all tall compared to a regular Macintosh one. Let's reboot. Please reinsert diskette when it's released as a safety precaution. Diskettes are always released during a restart. There's a whole lot of activity going on considering it's just rebooting. So how am I supposed to get the disk out of the drive? I mean, I know the drive gear is bad, but it doesn't know that. I was reminded by Alex this was actually a problem on the Mac 128 and 512 as well. If you tried to use an 800K drive, there were a couple extra signals that would cause issues with the ejecting. So Apple made this special yellow floppy cable with the yellow stripe on it, which has a couple of the signals removed, which allows the disk drive to work properly. So I went and found one. I knew I had one in my stash and I tried it on Lisa, and sure enough, now the disk ejects properly. Perfect opportunity for me to hit the reset button so I can swap over the integrated WAS machine. If I can find my chip puller, here it is. Okay, so this is the IWM 004D1, the one that came from the Apple II card. Let's go back to the Mac SE one. Okay, the chip's back in. Let's power the system up. Let's see if it boots. I mean, maybe we'll be back to our error 47, who knows? 57, whatever it was. Okay. Oh, I was like, it's not working. Yeah, it's because there's no disk in the drive. Hello. While I wait, I'm going to install this chip back into its home in the original board. The Apple II Lyran card. There it goes. Because it definitely appears that the 0043 IWM from the Mac SE seems to work fine in the Apple Lisa. There it is. After much waiting, the system is booted up. So that means that this Mac SE IWM definitely is working properly. Yes. Very exciting to actually see it boot to OS. I know it's not quite the desktop, but it's definitely loading the operating system, and that's awesome. So clearly the next step, which will be in the next video, is I'm going to plug in the profile hard drive emulator, and we're going to try to boot into the full running OS on this so I can actually see Lisa OS working on this machine. Other things we can test out in the next video will be the other 2 RAM cards that I have, see if those are both working or not. And then there's obviously a little list of things I need to fix. So there was the problem with the trip breaker, so I got to add that to the list. And then there's the sound that's not working. I think that's really the main issue that I have left. It's really cool to know that my cable harness that I made definitely works, so that's great. The power supply is stable, other than the fact that we tripped the breaker that one time, but that's not related to the operation of the power supply. So the computer is stable, it's not crashing. This thing has been running for hours and hours and hours today, and it's rock solid, and that is exciting. It's great to know that the keyboard adapter I bought totally works as well, plus the cables and all that stuff. Oh, there's the power light that I got to fix, so that'll be in the next video as well. And I'm probably forgetting something, but yeah, there's still plenty of work to do. But I'd say the majority of the hard stuff has now been accomplished. And that is really exciting to me. And I can't really believe that this machine is to this point, because part of me didn't even believe it would ever get to this point where I could load Lisa OS, but I'm nearly there. I'm really nearly there to having a complete, fully assembled Apple Lisa 2/5/10 hybrid kind of thing. But that doesn't matter. That's on the inside. And yeah, this is so awesome. So a huge thanks to everyone who's been helping me out, especially Alex, who gave me the power supply and the boards. And then Jared, of course, who sent in all the parts. And then, of course, AJ, who gave me the machine in the first place, the whole Lisa. And then all the online resources that have been super helpful. And yeah, and all of you. So thumbs up if you liked this video, thumbs down if you didn't. Huge thanks to my supporters. Subscribe if you haven't already. You know, the usual YouTube junk. And I guess that's going to be that. So stay healthy, stay safe, and I'll see you next time. Bye-bye.